In this segment, we're going to talk about the first law of thermodynamics. We're going to continue our discussion and we're going to talk specifically about how energy can be transferred across the system by heat transfer. So, first law is also known as the conservation of energy, and it says that the change in energy stored by the system is equal to the net amount of energy that's transferred to the system across the boundary. Energy can be stored by the system as internal energy, kinetic energy, and potential energy. And those are all properties of the system. So if you look at the figure below, you see a system, and that E with a subscript 1 represents the energy stored by the system at some state 1. Now let's look at the other side of the equation. So it says the net amount of energy transferred to the system. And energy could be transferred by work, by heat, by work, and if we've got an open system, by mass flow. And we're going to focus on closed systems for the first part of this semester, which would leave out the mass flow, so we'd only have energy transfer in the form of heat and work. So let's look. Oh, and heat and work are not properties. Once they transfer across the system boundary, they can certainly they transform into other forms of energy, internal energy, kinetic energy, and potential energy, which are properties, but heat and work are not themselves properties of the system. So it's incorrect, for example, to say that a system has heat or contains heat. Now let's look at this diagram or this animation here. So E1, the energy contained by the system at state 1, and then we transfer heat and work across the system boundary, and now the energy contained by that system is E2, and the change in energy because of that heat and work being transferred across the system boundary is delta E, the change in energy stored by the system. All right. So let's focus specifically on heat transfer. This is energy that is transferred due to a temperature gradient. So if you have no temperature gradient, if you don't have a temperature difference between two bodies, you do not have any heat transfer. So let's take these two blocks. You've got block A and block B. Block A, let's say it is at a higher temperature than block B. And heat is always going to flow from the hot to the cold. So heat is going to flow from block A to block B until those blocks are at thermal equilibrium, at which point you have no heat transfer any longer. We have two ways of indicating whether heat is going into or out of a system. Sign convention is the one that we're going to use predominantly in this class, and it gives us the sign convention uses the sign of Q, which is the heat transfer across the system boundary, uses the sign, whether it's a positive or a negative one, to tell us whether heat is going into or out of the system. So if we have a system, if heat is being transferred into the system, Q is a positive number. If heat is going out of the system, Q is a negative number. We can also use subscript convention. And in this case, we won't use the sign to tell us whether heat is going into or out of the system. We'll use the subscript. So Q net in is equal, that's the net heat transfer into the system across the boundary. This is equal to any heat transfer in minus any heat transfer out. So Q in, that's heat transfer into the system, that's a positive number, and Q out is going out of the system, but it is also a positive number. So both of those things are positive numbers, and what tells us whether it's going into or out of the system is just a subscript. Now, like I said, we are primarily going to focus on the sign convention, but when we get to cycles, we'll talk about subscript convention just a little bit, but primarily in this class, sign convention is the one that you'll use. Both of them are correct. It's really a matter of preference and convenience which one you choose. Units and notation. So Q, capital Q, is in terms of kilojoules or BTU. So that is in terms of energy. But we can also express things in terms of energy per unit mass. And for this, we're going to use a lowercase q. Just like when we talked about internal energy and kinetic energy and potential energy, we had, for example, with internal energy, you had uppercase U and lowercase u. Lowercase u was kilojoules per kilogram. Uppercase U was kilojoules, so same kind of notation as what we've got going on here. Sometimes you're interested in the heat transfer rate. How fast are you transferring heat? And in that case, you use a Q dot, and it's heat transferred per unit time. So let's kind of recap what we've got so far. Energy can be stored by the system as internal energy, kinetic energy, and potential energy, and it can be transferred across the system boundary specifically for a closed system in terms of heat and work. For work, we use W, uppercase and lowercase w, depending on what units you're talking about. And since it's a closed system, you don't have any mass flow, so you don't have to worry about that. So let's put everything together, and here's our first law for a closed system. Left-hand side of that is the energy stored by the system. The right-hand side is the energy that's transferred across the system boundary into that system. You can also express it on a per mass basis by dividing through by mass, and in that way you would have everything in terms of lowercase letters. Delta little u, and those u values, you can look those up in tables, for example. Let's work a problem. So we've got water in a rigid tank, and it's heated up from some temperature and specific volume to 3 bar. No work done on the system. Determine the heat transferred to or from the water during the processing units of kilojoules per kilogram. So I'm going to write my given, find, assumption, solution. Here's my given. I've got water in a rigid tank. I don't really know what that rigid tank looks like, but I'm going to just draw it as a box for simplicity now. And anytime you've got a process, go ahead and when you write your given, write it just like this. It makes your life a lot easier. Write what you know about the initial state, what are the properties you know about that initial state, and the final state. So state 1, my initial state, I know the temperature and specific volume. And my final state, I know the pressure. Let's see what else I know. No work done on or by the system. That means W is equal to 0. And that's all I'm told. I know that I need to find Q in terms of kilojoules per kilogram, so that'd be lowercase q. And I'm probably going to have to make some assumptions to solve this problem, but I'm going to leave it blank for now because sometimes you don't really know what assumptions, what simplifications you need to do to solve the problem until you actually get to it. So I'm going to leave it blank for now. First thing I'm going to do is I'm going to apply my first law for a closed system. And I know it's a closed system because it's a tank. And I'm not given any indication that that tank has a valve that's open or anything like that. So in this class, when you have problems involving tanks or piston cylinders, unless you're given some sort of verbiage like that there's a valve opened or something like that, you can go ahead and model it as a closed system, meaning the mass of your system is not changing. So, all right, so my first law for a closed system, there it is. And I'm told that the work is 0, so let's go ahead and get rid of that and simplify things. And now let's see what else I can get rid of. What other assumptions can I make? Well, it doesn't look like this tank is changing in elevation, right? So we don't have any changes in potential energy, and nobody's carrying it around and speeding up with it or slowing down with it. So I don't have any changes in kinetic energy either. So I'm going to go ahead and get rid of those. And all I've got left is delta U and Q. And now I need to put things in terms of little q. So I need to isolate mass. So instead of having delta big U, I have m times delta little u. So delta little u is in kilojoules per kilogram. Mass is in kilograms. And then I need to divide through by mass and get myself something in terms of little q. And anytime you have a delta in this class, it's what it is after minus what it is before. So little q is equal to u2 minus u1. And there is my governing equation. I'm a third of the way there. Now I need to fix my states at state 1 and state 2. And in order to look those properties up, because I've got water and I've got thermodynamic tables at my disposal, but in order to look those properties up, I need to be able to fix my state. So I need 2 independent intensive properties. So what intensive properties do we know so far? We know temperature, pressure, specific volume, quality, and we know internal energy. Okay, we also know kinetic energy and potential energy, but that's not going to help me fix my state in those tables. So, well, I know that I need to find internal energy, so that's not going to really help me, but let's look at state 1, see what I need and see what I know. I know temperature and I know specific volume, and I know that those are always independent of one another, so that's enough to fix my state. Now I need to fix my state. And in order to do that, I need to figure out what phase I'm in. So I am going to go to my saturated tables, not because I'm assuming it's saturated, but because I need to figure out what phase I'm in. So I go to my saturated tables that are organized by temperature at 100 degrees Celsius, and I ask myself, is my specific volume in between V sub F and V sub G? Because if it is, then I'm two-phase. And it looks like, yes, I am. So I am saturated because my V1 is between V sub F and V sub G. So because I'm two-phase, I know my internal energy, U1, is a function of quality. Great. So I can pull U sub F, which is 418.94, and U sub G, 2506.5 kilojoules per kilogram. I could pull those right off the saturated tables, but I don't know quality yet. I need a way to find quality. Well, because I'm two-phase, I know that my specific volume is also a function of quality. I know V1, and I can pull V sub F and V sub G off my tables, and I can go ahead and solve for my quality. So my V sub F, that's 0.001043.5 meters cubed per kilogram, and V sub G is 1.673. Just be careful about that V sub F value because it's times 10 to the third, so just be aware of that. So when I plug in my numbers, I get 0.59748. Perfect. Now I'm ready to plug that into my equation for U1, and I get 1666.27 kilojoules per kilogram. Great. So I've got one of those things. Now I need to figure out what U2 is. Still need two independent intensive properties to figure out U2. I know temperature, pressure, specific volume, quality, internal energy. Those are all intensive properties. Now let's see what I know about state 2. I know pressure. That's it. I need another something to fix my state. So I probably need to assume some things. I go back to my problem statement, and the problem statement says that I have a rigid tank, which tells me if it's a rigid tank, that means that the walls are not deforming, and so the volume of the tank and the volume of the water are not changing from state 1 to state 2. Well, volume's not really an intensive property, so I need something else. I also know that I have a closed system, and a closed system, by definition, the mass doesn't change. So I can use that information to figure out the specific volume of my water at state 1 and state 2, and I see that my specific volume doesn't change either. So V1 and V2 can be assumed to be the same. So now I have two independent intensive properties, and now I'm ready. I'm ready to go fix my state. What's my phase? Let's go to my saturated tables and figure that out. So here's my saturated tables for water organized by pressure. I go to 3 bar and I ask myself, is it saturated? Is my specific volume between V sub F and V sub G? And it looks like no. My specific volume is greater than V sub G. So that means I am superheated. So I need to go to my superheated tables. Let's get out of here, go to my superheated tables. And remember, those superheated tables are organized in blocks of pressure. So I go to the block corresponding to 3 bar, and I just look down that specific volume column and see, well, where's 1? It's not on there. But I do have a specific volume right above and right below that, 0.969 and 1.032 meters cubed per kilogram. So my answer is I need to interpolate. So if you forget how to interpolate, go back to the segment talking about interpolation. And if I interpolate, I ended up getting 2932.99 kilojoules per kilogram. So looks like I got my U2. I just plug everything in, and it's a positive number, which indicates that heat is transferred into the system, which is kind of mirrored in the problem statement. So I am all done. All right. Well, thank you for watching.